Okay, so welcome to our third day for this this summer school. So today George is going to give some of the lectures and also Panos Stinis. And so one of the topics for today is Mori-Zwanzig. So we talked about Mori-Zwanzig before, and it's a very powerful technique that allows you to build mesoscale models from fine-grained dynamics like multidynamics or information-based simulations at a very fine scale. So therefore it's very relevant, obviously, for this topic of mesoscopic modeling. So George will be giving the first lecture.
So, like Eric said, Mori-Zwanzig has been around actually for quite some time. It's in the 60s, and later on, so I'm giving the first lecture. It's mostly using Mori-Zwanzig as a computational, the formalism as a guidance to build coarse-grained models. However, Mori-Zwanzig can do much more. In this, following my lecture, Dr. Chan Joaquim here from Lawrence Berkeley, will talk about the Mori projection, the Zwanzig projection, many things that you will not understand in my talk. I'm sure he will explain. I've seen his lecture, and it's very pedagogical. And then in the afternoon we have two lectures by Panos, who concentrate mostly on PD. So Mori-Zwanzig, as I said, although has been around since the 60s, it has sort of been resurrected around the year 2000, where Shor and his collaborators wrote a paper how you can use Mori-Zwanzig in constructing computational models or looking into small scales and the relation to the resolve scales and so on. So Mori-Zwanzig can be used to derive, to do lots of things, derive coarse-grained equations, so that's the topic that I will cover. Analyze systems with memory. I will talk about that, and also Dr. Kim will also talk about this in some depth. Construct reduced order models, detect singularities, and quantify uncertainty. 3, 4, 5 will be covered, I think, in the lectures by Panos. So the material here, I mean, the literature on Mori-Zwanzig is not so extensive, so what you will see here is pretty much it. There's lots of references to cover it. It's a new field, but you will see some of its potential. So I talked about the hierarchy of mathematical models yesterday, how you have the mathematical models on the side, and then the numerical models on the side. And the top-down approach would go from continuum, which, like aerodynamics, would be top-down approach. The bottom-up approach, which we will pursue here, is starting with MD and coarse-grain it. Okay. Now, you can think of also of a PDE, where you start with a PDE and you try to come up with a low-dimensional system of that. So a dimensional, this basically implies dimensional reduction in different forms at the discrete level with particles or at the continuum level with PDEs. So that's what we will do. That's one of the objectives in this lecture, is how we can start with molecular dynamics and build a mesoscopic method, a coarse-grained method, like dissipative particle dynamics. There's a lot of confusion. What is coarse-graining in general? For example, you will find in the literature that people say it's a coarse-grained molecular dynamics. So what does that mean? It means that, and that has been used a lot in soft matter literature, it means that they basically use the Lennard-Jones potential at larger scales without any respect to all the terms that are missing when they do that. You cannot just simply map a nanometer to a micrometer and say that's coarse-grained molecular dynamics. So my last slide will show you the difference between what is the right thing to do and what is coarse-grained molecular dynamics, which is not always right. So just to fix ideas, and I know not everybody is familiar with particle systems. I will introduce some concepts, and later on Chanho Kim will also elaborate on this. But let's start with the basic of all, and that is the pairwise distribution function, or radial distribution function, or RDF, or GeoVar, and how the GeoVar symbol has been used almost in all literatures across fields. So the idea is to characterize, this is a metric to characterize the structure of the fluid or the solid, or a granular material if you like. So it's very, very useful. It can be measured with X-ray or synchrotron or neutron scattering technology. And here's the definition. So think of a bunch of particles like that, which made up the matter, the solid or the fluid, or the gas for that matter. So we concentrate at one location R, and we construct a spherical shell around that. So this is supposed to be a spherical shell with thickness dr. So we can basically, if you multiply by density, the rho gr is the condition probability to find another particle at a distance r from the origin, from where you measure your GeoVar. So that's why it's called probability, because it tells you how likely it is to find some particle there. So you can understand that would relate to the structure of the fluid, and it's very easy to construct it at the summation. But this is exactly what I said. Here's the definition, that you take in that spherical shell the number of pairs that you find the particles, and then you divide, you normalize by the volume of the shell. So just to have some idea of what different types of materials would correspond to, you start with so you plot this GeoVar as a function of R from the origin, right? So an ideal gas will correspond to GeoVar equals 1. So that's sort of your reference line. And then if you have a solid or a crystal, a liquid crystal, let's say, it would be, because you have a lattice, this fluid don't change too much, so you have like spikes. Here I have for the solid, but it could be even a single line, like a spike here, spike there, spike there. So this blue would correspond to some hard material, let's say. Then the liquid is plotted with the black curve here, and then the gas, the dissipative gas, for example, would be the red. So all these are important. For example, how many times you cross the line, and so on. That defines exactly what type of material you have. Now, why is this important? Because when we coarse grain, I start with water, and I start coarse grain it. I don't want to get molasses. I still want to get something which looks like water. In other words, I have to respect the structure at this level. So GeoVar is the first thing to, of course, you also need to worry about the equation of state, and you need to worry about dynamic properties, but this is the basic thing. In addition, GeoVar is very useful because you can, based on that, you can define important quantities like the internal energy. See, the integral contains GeoVar, the pressure. Yes, they talk about corrections of the pressure. And what happens if you have a truncated boundary, GeoVar that relies on this spherical domain, spherical support. If you truncate the domain, you have a defective GeoVar. You don't have a full support. So you have to be careful how, when you approach a boundary, how you change GeoVar, and then how you change the pressure itself. That's why you need to deal with forces perpendicular to the truncated boundary, which I was talking about yesterday. And finally, the static structure factor is something that is used, and that shows how a material scatters an incident wave, and that is also defined based on GeoVar. So the structure of the fluid, of the material, depends on that. Another quantity that we'll be using a lot today, both in my talk and Chanho's talk, is the velocity autocorrelation function. Also, Paul Landsberger, in the first day, he introduced that. Now, here we will compute it from first principles, as you will see, at short times and long times, and the behavior of the velocity autocorrelation function, VACF, is different at short times. So at short times, we say like an exponential. Gamma would be some friction coefficient, like, let's say the Stokes drag on the particle, time, and then m, the mass of the particle. So you have a very fast decay. And then for a long time, it depends if you are in the open space, no boundaries, open boundaries like the Odyssey, or if you are very close to the wall, you get a C of t decays algebraically, not exponentially anymore, algebraically. And this exponent in open space is the dimension of the space. So in 3 dimensions, it's 3/2, but it will also be t to the -1 in 2 dimensions. So this scaling is important. Now sometimes this is called the hydrodynamic scaling. So you expect, if you conserve momentum, that you will recapture that with the right calculation. As I said, if you're very close to the wall, that scaling could change to something faster. So in a combined form, you can write C of t as the 2 asymptotics forms that I have. There's this correlation is related directly to the flow structure. For example, in his talk, Dr. Kim will discuss how this VACF relates to the structure of the fluid, vortex generation, and other structures. And that can be only obtained, not from top down, but from very fundamental non-equilibrium molecular dynamic simulations carefully done. So that's sort of new work that Dr. Kim will present. But the correlations have been known for quite some time. Then yesterday we also talked about fluctuation dissipation theorem. Now it's a practical theory. Sometimes they say theory is a practical tool. This is one of these things that actually the theorem is very practical, because you can have fluctuations and the variance of the fluctuations, if you like, the amplitude of those fluctuations is related to dissipation. Unless you have some sort of a balance of that, you're not going to go to equilibrium. Okay, so this a classical paper, if you want to go deep into this, is this paper by Kubo, the fluctuation dissipation theorem, 1966. You can use that as a reference. So there's some technical things here, but basically, if you look at a system with Hamiltonian H0 and mean position average X0, as you can see here, you denote the spectrum fluctuations. You denote by spectrum, spectrum X, Sx. So there is a specific relation. If you perturb that system with some force f of t, then you can write this equation here, and then you can write this other equation here, Sx. This is some function of the susceptibility function, but you can have the spectrum here related to the imaginary part of the susceptibility. So from the physical standpoint, what this says that you have the fluctuations, which are in the spectrum here, relate to the energy that dissipated, as shown by the right-hand side. But at a higher level, what you can think of is that we have fluctuations. Then in order to have equilibrium, you have to balance those fluctuations with some dissipation of energy at the right rate. So that's very important, because when you parameterize the system, you don't have arbitrary parameters let's say on the random part or the dissipative part you will get from the physics of the problem, or from, as I will show you, from the velocity autocorrelation, the force autocorrelation. So practically, again, here this would mean that for a particle system, this sentence down here that you may not be able to read, for a particle system, the canonical assembly is expected only if the fluctuation dissipation theorem is satisfied. So you have to sort of invoke that theorem explicitly for systems with memory and systems without memory. That may complicate things, but it's also useful. As an example, and I show you this slide yesterday, but I went over this very fast, is let's look at the DPD system. The DPD follows Newton's law, mass times acceleration. The right-hand side has all these forces. Okay, so this is a conservative force that comes from the gradient of Lennard-Jones, or an effective potential, not necessarily that, but corresponding to that, sometimes repulsive bonding potential. And then this pair of forces, the dissipative force and the random force, is exactly what I said. Here's the dissipation through the Stokes drag, let's say. These are the envelope of interaction with velocity. So that's the dissipation force. And here is the random force, and the fluctuations are described by the amplitude of fluctuations described by this. Now, if you together those two forces play the role of what's called the thermostat that keeps the kinetic energy. And kBt here is not actually temperature, is the sum of velocity squared, fluctuations. But if we look at up here, these equations here are derived based on the fact that we have the fluctuation spatial field. So it's exactly what I said. Sigma squared, which is the variance of this fluctuation, is related to the friction at a certain level of kinetic fluctuations, kBt. And correspondingly, this envelopes of interactions here, which says how far this particle interacts with, think of this as what the Mauro called yesterday, horizon or cut-off distance and so on. It's an envelope of interaction. Those are all also related. So you see right away it's a practical thing to do. So that's sort of by the way of introduction. I will proceed with this topic. So I'll talk about coarse graining of a system, a simple fluid, and Lennard-Jones fluid, but also a polymer. How do we coarse grain a polymer? And as I said, we'll be looking both at static properties and dynamic properties. Both dilute systems, density small, but also density large. And that's a very big distinction, because as you will see, there are issues when you coarse grain dense systems with memory effects. Okay, so in general, there are two ways of going about coarse graining. The reverse coarse graining procedure and then the forward one. This is most of the times people in physical chemistry, or in polymers in particular, they would use something like that. You have a molecular system that you try to coarse grain. You set up some target properties. Obviously, you're going to lose information as you coarse grain, but you want to maintain certain key properties for that function that you have in the application, that functionality. So we're talking about here functional fluids, right? Fluids that have more than viscosity, more than a shear modulus, so or viscoelastic material. So we want to preserve that functionality. It could be, for example, the dynamic properties like viscosity, diffusivity, and so on. So we target that, and then we set up an iterative procedure to find what are the right parameters in the force parameterization that we have. So we will go through an optimization loop, and the levels of sophistication of optimization vary. Now that doesn't guarantee, you may be lucky, but it doesn't guarantee that other properties that you're not targeting will match. That's very important, okay? Now, if you target specific properties like viscosity or another property, equation of state, or G of R, let's say you target G of R, if you target G of R, you will be able to find exactly the potential for the conservative force, in other words. That's called, that's a pretty standard method in the literature. It's called iterative Boltzmann method. However, that doesn't, if you have that right, the conservative force, it doesn't tell you anything about the viscosity, it doesn't tell you anything about the velocity autocorrelation function, which, as we'll see, is very important. Now, the other one, it's more recent, is to sort of do a lot of work, lots of molecular dynamics simulations, and build a database and use that to construct models with the guidance of Mori-Zwanzig that I will show you. So we'll go through this, and I'll show you an example of this also as well. This now has gained a little more interest because of machine learning and Bayesian frameworks that have been formulated. So this is also becoming popular again, because also we can deal with more parameters. Okay, so let's look at a specific example of coarse graining a system like that. It's a complex system, as you can see. It's an all-atom system. We're not going to do this. The state of the art is not there yet, but this would be perhaps the target. So we want to coarse grain that. If you look from afar, the topology is about the same, but there are some atoms that are missing. The microstructure will basically remove the microstructure. Now here's irrelevant variables are eliminated. That irrelevant should be considered carefully what is irrelevant, because what is relevant for me may be very relevant for you for some other function. So you have something in mind, so basically you end up with that. So somehow you don't just eliminate, you group atoms together. So, but in the process, what you eliminate is the microstructure. So think of a molecule, and I will have an example later. It consists of, let's say, of 10 atoms. I can make the whole molecule as one particle. So I have the degree, of course, graining is 10 to 1. I'll refer to that. Now, of course, we're very aggressive and we want to have like 100 to 1, 1,000 to 1, because that, we can finish faster. But when you will see, there's a price to pay when you're too aggressive. Okay, so we'll see that also in the examples. So I have an example here that was created by Juan Ley. I don't know if he's here. Right here. It's a very pedagogical example. So I want to play this for you. So it's very, very simple. It's high school physics. There are lots of high school kids here. Too many. Crossing the roads, in fact, that's like have to wait for 5 minutes just to cross. But anyway, let's look at a chain of elastic spheres colliding. So I have 20 spheres, and I want you to pay attention to the centers of those spheres colliding. Okay, so that's the way to describe. So that will be my detailed system. If I can play that. Okay, so we follow the centers of this, and you see elastic collisions everywhere, right? 20 spheres. So I have 20 degrees of freedom. That's the point if I have the centers of the spheres. And you can see all the collisions are elastic. It's a nice thing. Okay. Now, here's what I want to do. I don't really want 20 degrees of freedom. I only want 5 degrees of freedom. So I'm going to group 4 spheres into one virtual big sphere, which I will color it green. Okay, so I'll take the 4 here, and the 4 here, and the 4 here. It's sort of natural, okay? So now, I don't want you to look at in the next movie, don't look at the blue colors, only the green colors. The centers of the green colors. Okay, so let's look at that. And the green spheres, or circles. So, I have a question now. What do you see? Do you see that these green spheres collide elastically? No, right? So, but I want to describe an elastic system. I group the spheres into these green spheres. And these green spheres now are viscoelastic, right? So I change the system. So I cannot use the same elastic equation to describe this because with the fewer degrees of freedom. So well, I have to say, and I'm an engineer, all my degrees are in engineering. In all engineering systems, we don't pay attention to it because somehow they work in practice, they say. But going from here to there, it's a different term. You have to, it's a low dimensional description, and we don't care about it. So I'll give you another example. I think this is from Panos or Stinis notes. I put it here because it's early on. So this is, again, high school, Stanford High School. So let's take this 2 ODs, linear ODs, and we'll eliminate Y. Okay, we'll eliminate Y, so the 2 degrees of freedom will become 1 degree of freedom. Now I can solve for Y. I substitute here. So dx dt here is now I have only 1 degree of freedom for x. The x is here, and where's Y? Well, Y left a footprint in the initial condition here. But it also left this term. What this term is? It's the history, it's the memory. It's the memory of the trajectory of Y, right? So that's here. So that's sort of what's going on here. We have a dense system, we eliminate degrees of freedom. We have to include these memory terms back into the system, okay? So that's a simple system, and that shows you what happens. So dimensional reduction, and that's what I said earlier. I found myself in many projects doing dimensional reduction, just neglecting all this. But you can see there's a memory term here. And so that's kind of important, okay? So that's what I want you to get as a first impression, that you cannot just arbitrarily reduce dimensionality. Everybody wants to reduce dimensionality these days because we like high dimensions on many parameters. So let's do that same thing now for an MD system, a molecular system. I group it like this. So this is one big particle, these big particles. So now I will set up rules for these big particles, and that's what DPD or another mesoscopic method would be. So if I describe this with Hamiltonian, I will use lowercase letters, P and V for kinetic energy and potential energy. Pi will be the momentum of each individual molecule. And then what I do, I group them. So Ri will be the individual particles, Pi the momentum of individual particles, and V is the potential of this, let's call it the atoms for now, or molecules, but then I construct the particle, the big particle. I have this cluster of particles, or a cloud if you like. It will have a center that is defined like this from the coordinates of the small particles, and its momentum will be the sum of the momentum. So now I still have an exact Hamiltonian, but I will plug in, I will try to rearrange all the terms so that I write the Hamiltonian in terms of these variables, the capital P, because this will be my coarse grain variables. Intuitively, I choose that. So since I have my coordinates were Ri, and then I have the momentum, I do the same thing for the clusters, the virtual clusters, if you like. Now, if I write the Hamiltonian separate what I can write in terms of the capital P and capital R, I get this term, the kinetic energy, the potential energy, and then I get all these other little terms. These sort of the leftovers. I cannot write those, I cannot express those in terms of P. So here's what I have. I have the exact Hamiltonian of the system. I write it in, let's say this is my green sphere now, but then I have this microstructure still here that bothers me because I don't know what to do with it. So what we will do, would like to sort of project that into some subspace so we can eliminate at least part of it or represent it in a different way. So that's what we are after. So let me just give you a brief review. I'm sure later on Panos will derive this. In the first day, Juan gave a derivation of this equation. But as I said here, I'm not after analysis of this equation, I want to use the equation in a constructive way as a computational platform to build models. But just to sort of clarify the notation, let's start with a system, a nonlinear system of ODEs, and phi I will go from 1 to n, but I break up phi into two groups. This will be the coarse grain, the resolved variables, the capital, if you like, the capital letters that I used before, and the tilde will be the ones that are the small scales, what I call earlier irrelevant scales, but a better term is smaller scales. So I separate the phi into two parts. So then I follow some equation, the Liouville equation, as I said yesterday, and then you write in terms of you write the solution in this exponential form. Then you define this projection operator as a average, as an expectation of G condition on this data on the resolved part of the unknowns. And then Q will be the complement of that. So P plus Q equals I. So you plug in here, you do some algebra here. I think these are the same steps that Panos will explain much better than me. But basically, you present this exponential now in terms of the P and Q projections. I haven't defined exactly the projection yet and the quantity yet, but you derive this generic equation, which is exact. You haven't made any approximation yet, and it's written in terms of some operators P and it's orthogonal Q. And it looks like a little bit, not like exactly, but a little bit like the one that they have for the two degrees of freedom. It has a memory term here. It has another term over there, another term there. So you cannot do very much with this equation, so you have to make some assumptions. But this equation is exact. It guides us. The Langevin equation will be derived easily from this. The generalized Langevin equation looks like that, and many other equations that we haven't discovered yet. So let's look again at that Hamiltonian system that I had, where I have the mass. I introduce also the capital mass, the mass of the cluster, I would be the cluster. I use the capital letters to show the cluster. It consists of many particles. Think of the cluster consisting of 10 or 20 particles for now. And then if you define some phase variable here, you can make the projection operators a little more specific. You go through here, and you derive an equation. It's not as trivial as I show you here, but it's a very nice paper by this Japanese team that I met here first time in Toyota, when I visited the research group of Toyota. They have presented this paper. I've just written this paper, and I was amazed that in Toyota they do Mori-Zwanzig. But anyway, this equation is similar to what I showed you before. I will explain this term, the omega r. It's some normalized partition function. It is the memory term, and then there's another term which I write in terms of some force. So that term ETQL QLA is basically we assign it the name random force because it doesn't quite relate to the resolved variable. So again, let's just fix ideas. We have this system. If it's a polymer, it's much easier to see because you have you have bonds, so all these molecules stay together. So it's easier to see schematically what's going on. We go from the Hamiltonian with the small letters to the Hamiltonian of the large letters. We project that and we get that. And we get the final form that we want. So this is the form that I want to talk about. Now we have to make some approximations. So this is sort of where the approximation will start. And the first approximation is because I have to deal with this interesting but really nasty computational term. This term also has to be dealt with. The first term, it turns out, has to do with the configuration, all the configurations of the space corresponding to the location R, and it involves the potential energy of the atomistic system. Therefore, it relates to the conservative force, which comes from the potential. The first approximation is that we will introduce pairwise interactions. So that's a very significant approximation. The reason for it is the computational ability, that you can computability that you can compute this. So I take this force here and I decompose it into pairwise and also this other random force. The second approximation is that I would say that if I have two clusters, that this random force delta F ij, and I'm at the cluster I, and I talk to j and a k, so this correlation is 0. So in other words, the force Fij between the cluster I and j only depends on the relative center of mass positions of these clusters, and is independent of the position of the rest of the cluster. So we also have just the Rij there, and we don't. So we don't have many body approximations. The moment we do this, we throw away the many body interactions, for example. So that's an approximation, maybe draconian or not. It has to be checked, and that will depend on the system. And we'll see that it could be important, but in some cases it's negligible. So the first term we associate with the conservative force, as I said. Let me just go forward and show you what omega. So it's a ln of omega r. What omega r here is what I said earlier. Is think of all the configurations of the system associated with this location r, e to the minus b u. U is the potential of the atomistic system, and then it's normalized. So that is the conservative force, what we call conservative force before. Then we have the second term, which is a dissipative force. I will explain that a little better. Now, this math here is just to show you that because of the two approximations, the correlation, the independence of the clusters, and the pairwise composition, I can write this in terms of Ij down here, the pairwise force, and I have here a definition of the kernel, but I will get back to it. So in summary, maybe this is what we have. We have the rate of change of momentum on the left-hand side is equal to some conservative force, which you have to compute from some potential or some effective potential. Okay, that's what would go into molecular dynamics, that's the term. But the extra terms, dissipative force and random force, which came directly from the Mori-Zwanzig, and we saw them in the ad hoc DPD formulation, also come from this part. Now, we can have lots of approximations. We can say random force is some white noise, but would that be okay? It's an easy choice, and we'll see that that's not always okay. The dissipative force will say, well, what I see here, this is an integral that has the force, the random force of the correlation. This is the random force right here. So I have already taken care of the fluctuation dissipation theorem by making this equal to that. So I have this term, so I have a autocorrelation function, force autocorrelation function. So one idea is to sort of say, okay, let me assume some kernel with that. So I don't have to actually compute it. And then you can simplify things. Another one would say, this is a really nasty nonlinear product. Maybe I can assume some separation scales, and I can take the velocity, which is momentum over mass, I can take it outside, and then I just have to integrate that autocorrelation function, and we can do that. That autocorrelation function, the integral of that will be gamma, the friction that I had before. So those are simplifications I will be doing. So I can rewrite the same thing in terms of a kernel, which I will define again. I define it down here, a memory kernel in terms of this beta is, by the way, is 1 over kBt. It's just a kinetic energy or thermal energy. Okay, so this is what we have to go by. I show you this, and here we have a question. So we derive an equation now, and in the first day I said that we have no equations for mesoscopic dynamics. In Mesoscale we don't have equations. This equation is not good just for fluids, it's also for polymers, it's good for solids, it's good for turbulence, okay? So it's a general equation, and it's really up to what type of approximation we have to make, especially what I will assume here, and would I separate the velocity from the force autocorrelation function. So that's a question that we pose. Is this a general coarse grain equation? The answer to that is yes, given these assumptions that I introduced, but it's not a general in the sense that it's not universal. It can also fail, okay, because we don't include, as I said explicitly, too many body interactions. The memory effect is still there under that integral. So let's look at something really familiar. You can derive here the Langevin equation relatively easily. Just
it kind of depends how. I mean, this thing about saying, oh, we're making approximations and so on. I mean, you can also say that. I mean, you can also rephrase this as differently by saying, okay, here's the form of my equation, and instead of writing the expectation, you just have some kernel function here, some function of t minus s plus the noise, and then in some sense, I mean, there is always a solution. I mean, the question is, how do you compute the kernel, and whatever is left goes into this noise? I mean,
you can
saying that you're making approximation is not
entirely. You can write it. So this way, I already took care of the fluctuation dissipation theorem. I can have a general kernel here.
Right.
So then you have to apply, any exotic kernel. Then you have to apply an explicit constraint that relates that to that last term.
Yeah, right. But then, in some sense, you. Right. Okay. Yeah. Sure.
Can I just make one other small point? Are you allowing for a state-dependent kernel? In other words, my current configuration.
Yes, and that's we'll get to that. That's the interesting part. That's the juicy part. But let's look at something familiar, the Langevin equation. How you can, and you may have heard of the war between Paul Langevin and not Paul Langeberg, not Paul Langevin, and Einstein. Who derived the most beautiful, one of the best derivations. But this one is straightforward. Let's take. Okay, so this is the assumption. I take this to be delta correlated in time, as you can see here, that kernel that we all talk about. And then this integral, if I just take this integral, there's no velocity here, but if I just take this integral, then I can compute it simply like that. So then I take the whole integral, the Dorian product, I make a Markovian assumption. I separate the scale, so I say this, for example, decays much slower than this. So I can compute this first, take this outside, and that then is this, which I will call gamma, and there goes my Langevin equation. I derive the Langevin equation, the conservative force, gamma, I know exactly what gamma is, 1/2 theta sigma square, and then I have the random force. So you have a one-line derivation of the Langevin equation from that, okay? So if you change this correlation, you will get something different. Now DPD is specific, this pair has these pairwise interactions. So the original DPD formulation assumed that you have forces along the center. But it's clear that if you make this canvas bigger, if you have lots of, if you pack a lot of particles and so on, you need to worry also about the perpendicular force. Not so much for the conservative force, because the conservative force, I told you, take this integral over all configuration, so the normal component will probably diminish, and experiments show that, numerical experiments, but the random component, the instantaneous, you have to separate into two forces, two directions. The one along, which is a parallel symbol, and the one perpendicular. And that's important because by doing that, you automatically introduce not one thermostat, but two thermostats. A thermostat here is a pair of forces that comes from the fluctuation dissipation theorem. It's the dissipative force and the random force. So I have a dissipative force and random force this way, dissipative force and random force this way. So if you look at the correlations, the assumed correlation, so this is again, specifically for DPD, one can develop another method by changing this. For DPD, you have a different type of correlation because it's a pairwise correlation, and you have two correlations because you have perpendicular and parallel, and you write it like that. So if you plug all this into this equation, then we have a new equation, the Mori-Zwanzig DPD equation that you can see here, whereas the conservative force, this is the old stuff, if you only assume parallel, but you have picked up all these extra terms, and you have to apply fluctuation dissipation theorem in both directions. So we'll test all this. So again, this is conservative force, dissipative force, random force, and I have similar things in the other direction. So let's do an experiment. The experiment will be, we'll take a Lennard-Jones fluid, defined here, the potential, and I have one of the first questions you have to say is how do you exactly, if it's a solid, right, if it's a polymer, you have bond interaction, so you can draw, this is my cluster, this is my particle. Now, if I have a fluid, a gas, and liquid, molecules come in and out all the time. So you have to define what is a cluster. So that's really tricky, and it's still an open question, but here is one possibility. And you have to use constrained molecular dynamics to do this. So what we do, and this work that was done in PhD one way, is to define, just like in a polymer, you have a radius of gyration, basically the size of the coiling of the polymer. You define some characteristic distance, I will call it radius of gyration, and then you constrain these particles, and you call that a cluster, all the particles inside there. So first we do a molecular dynamics with this constraint to find out the statistics of this. So the question we ask are this. Going from molecular dynamics to this mesoscopic method, what is preserved? What is lost? What's the conservative force? What's the dissipative force? What's the random force? And if we look at static properties, like the structure of the fluid, do we have it? If we look at viscosity, diffusivity, and other properties, do we have the same? Okay. Now, in soft matter, people have been using the following simplification. Instead of a Lennard-Jones potential, which is very stiff, and that's the reason why you take very, very small time steps, and therefore you cannot span you cannot cover large time scales, we use a soft potential, and typically we use a quadratic potential. So, and repulsive only potential. The attractive part is the negative part. So the question is, and that's what people who have been using DPD and other coarse grain methods have been using. And the question is, could we, from first principles, justify that? So here I have a plot that shows some of the results. Let's look at this first. So we take a relatively large cluster, some RG. I pack 10 particles in that one cloud, one particle, 10 small particles. So 10 to 1 is the constraint integration. If you plot 1 over kBt times the potential for different temperatures, you can see you have universality, all right? All curves collapse into 1, and basically it's a repulsive moment potential. The 0 is here. There's no attractive part. Although you start with a Lennard-Jones, that is this averaging, so to speak, this cross-grading gives you a repulsive volume potential. So that's kind of interesting to see that holds. But also, if you look at this here, I have another system where I pack the same number of particles in a smaller space. 0.95 is the size of this cluster, the radius. Exactly the same conditions. I see that that's not quite true here. In fact, there is a residual attractive part right here, the negative part. So it's not a repulsive volume potential. So that assumption is a mixed, and that it has mixed success, as you can see here. You can change the density. It turns out that this may relate exactly to the violation of that assumption of independent of clusters that we have, and the many-body effect, which is not as big in the other case. It's interesting to look at the dissipative forces, because the dissipative force is the one that represented by this middle term in the Mori-Zwanzig formulation. And again, I separate this into two parts. One is a relatively small but compact, which didn't follow exactly the repulsive only potential, conservative force. And then the other one would be for the larger cluster. So we're looking at two different things. So let's concentrate on this panel. This panel shows correlations. It first shows this force correlation here, and corresponds to those two curves in the perpendicular and parallel direction. So you can see a very fast decay of that, corresponding to the velocity of a correlation. And that's very important, because that was the assumption. The assumption was that I have a separation of time scales, so I can bring the velocity outside, and then I can take the integral. If I can now take the integral of this guy here, I get a gamma, the friction coefficient, directly from the integral of the autocorrelation function. And it's interesting to see that for the smaller size clusters, I get a gamma parallel, which is bigger versus time than the gamma perpendicular by almost factor of 3. Now, for the other side of the clusters, although I have still 10 to 1 cross-graining ratio, I see that the opposite is true. Actually, the perpendicular friction is bigger than the other one. So the other thing that I see is that there's still some separation of scales. The velocity of correlation drops slower than, or this decays faster, the force decays faster. So the Markovian assumption may be okay, but it's not as good as you can see compared to the left panel. So these are important considerations, because when I look at the dynamic properties, we'll see that there will be differences. But first, let's look at the fluid structure. Do I still have the same fluid, or my coarse-grained fluid is, as I said, molasses? So again, I want to separate the two clusters. The smaller size with these particles that doesn't suffer from this many-body effect. You can see here, if I compare the G of R, which has the form that I showed you earlier in the introduction, looks like this. The MD and the DPD, so the MD and the DPD for the same density match. So I reproduce the same fluid in this case. Here, in the case I have a bigger cluster, the same number of particles, turns out that for densities of 0.4, I reproduce the same, but you consider the discrepancy for the case of the high density 0.8 compared to the 0.08. This curve is not the same. So the many-body effect maybe is important here, but didn't allow me. This is a case where I don't have the same fluid, so it's not automatic. Now there's a way around it, because as I said, if you use the iterative Boltzmann method, if you know the fluid structure from MD, you can compute you can compute exactly the conservative force, but that is not consistent with the MD that you have. Okay, so the next question is the dynamic properties, and dynamic properties, we're talking about diffusivity, viscosity, and so on. So this is kind of also interesting. We'll look at the mean square displacement, the second moments of order displacement for different densities. And again, I separate to two panels, the left and the right. The left corresponds to the smaller cluster, right on the larger cluster. And again, you can see there's a very good agreement, right? The mean square displacement from MD and DPD is the same for different densities. And this is very consistent, and that's very important, with the velocity autocorrelation function. The velocity autocorrelation function is a little bit of disagreement, but that's very reasonable. The integral of this will give me the diffusivity anyway. Here, on the other hand, I have a lower density agrees MD and DPD. The larger density does not. And in fact, there is a large deviation of the velocity autocorrelation from the MD and the DPD. So I have some success, but also I have some failures.
George, I missed, how do you vary the ranges of gyration?
So this is for the, if you don't have a polymer where you have bonded interactions, you have to somehow define what is a cluster. Mm-hmm. So if you think of this fluid, right? How do I get this? So I take I arbitrarily say this is RG, this sphere. And I constrain these particles to stay there. So I move, that's my cluster. So I change that. So I change that to see, for the same number of particles, same density, what is the effect of that? So the larger RG means that these guys are closer to each other for the same volume and the same.
So the larger RG means that they're closer?
When they are closer, am I right? Because they
means it's more loose, and the small RG means a little closer pack.
Right.
When you're close pack, then the manifold effect is not that strong.
Right.
Loose pack, they're
Right.
very strong.
because you keep the you want to keep
So
the
this is when you run this constraint MD where you fix this RG.
you fix the RG, yeah.
So you can fix that, right?
Yeah, because there's no. I will contrast this with the polymer. In the polymer, there's no ambiguity. That's why we start with the simple fluid and we went to this.
Sorry, let me ask you another question. But if you fix the density, this RG is more or less fixed for a given number of particles. I mean,
Say it again.
if you have a fixed density, and if you take a fixed number of particles, that RG is more or less fixed. I mean, to what extent can
You define that. You define that in the way.
Yeah, but physically there is some sort of.
There must be, yeah. You cannot do it arbitrarily, right? Because arbitrarily big. Because so there's some densities that you do that you can. Okay, so let's go on with something more important. This juicy part, as I said. So we have looked at the Markovian system. The Markovian system is one where this memory kernel, this basically the correlation function, you write it as gamma times delta, and gamma is simply the integral of this autocorrelation function. That's how, which I call here memory kernel. The scaling factor is KBT. Now, and we went on to and these are the equations of motions. This is what I used just now. Now, if we go to the non-Markovian system, a system where there's no separation of scales, in other words, the decaying of the velocity autocorrelation, the decaying of the force autocorrelation is pretty close to each other. It may be different like the one case that I show you, but closer, then you have to consider this term explicitly. So the memory effect is finite, and the question is, how do you do it? Okay, so now remember, this is integral from 0 to t, so you have to go back all the way to 0. Or you can sort of fade the memory somehow, but you have to go, let's say, back 1,000 time steps and keep the configuration of the system, this here, and that requires a lot of memory. It's very, very expensive. So you can do a simple trapezoid rule to approximate the integral, but you have to, so you have all these terms now. This sum is basically this time integral.
Then there's some other. Now, the moment you do that, if you don't have this delta correlation, then the noise, because delta relates to k, the noise is not white noise anymore. So you have this compound difficulty that one, you have to take the memory, the other one, you have to generate color noise. And how do you do it? So here I wrote down the equation, so don't expect you to see all this, but this is the first part that we had, sum over the history, so t minus n delta t, and it goes up to 1,000. If you go all the way to a few millions, which is the simulation, then you cannot do this. But and this is work by a Japanese group that we reference in the references. But then there's this other terms that have these factors alpha, and this relate to the color noise. And these extra terms are here to guarantee that the fluctuation dissipation theorem is actually valid at every level of the configuration. So we'll talk about that.
Another question here.
Yeah.
So you have psi here and dw there. It's because one is just a scalar, and what's the
This one term, I don't remember exactly what this is. So that's the random force. This is for the color, right?
DW is a matrix, so generate.
The dw is a matrix now, ij.
but so and why is it the matrix versus the scalar?
Because the power direction is only one direction. The
Oh, yeah.
vector direction is have a flint. It's two-dimensional.
Oh, so it's a random direction.
Yeah.
So this will be a 2 by 2. This is just along the centers.
There's a paper with the details. It's published already. Okay, so okay, talk about the fluctuation dissipator theorem.
The important thing is here is that we have to satisfy this now in terms of the kernel, right? As opposed to just a delta
Correlation here, and then the question becomes, how do you generate color noise? I will skip the first method here. You can use Fourier transforms, but they don't work very well. So let me just define
here as Rn, the random force, and theta n, I have the kernel. So let's assume that I know the kernel, and I have to generate color noise.
So there are different methods to do this. One is to use this optimization. So you take the random force Rn and you write it in terms of this W, these white noises, and then you construct the correlation and you parameterize
The correlation here in terms of these alphas, which I write as Fn. Now, on the other hand, I have the fluctuation dissipation theorem, which I want it at every level to be valid. So theta would correspond to the k, theta n would be the kn, my kernel at kn. So if I make this and this close to each other,
and I can do like minimize the difference in the L2, let's say, that's how you can obtain, with all these parameters alpha that you introduce, then you basically have a way to handle the noise.
so for example, you can see here the alpha, we use 80 alpha coefficients here. To do this very expensive, turns out, but the results are very pleasing. Of course, you can verify the fluctuation dissipation theorem here in this with the autocorrelations. You get a temperature which is around 1, and you get a velocity autocorrelation function which looks the way you like it. It's for a specific application, so I didn't give you the background on this, but the point is there are ways to do it. There's some expensive ways there. I will show you also a simpler way that people here at Stanford, Hishan and Eric have been working on. So let's now move to another system, because this system is much nicer. It's a star polymer. Think of this as an octopus. You know, an octopus has a middle, the soma, right? And then it has arms. It's exactly what the star polymer is. So it has like N molecule, NC molecule. So a middle one and then the arms. This one is easier. So you have the middle one and then the arms. So 1 plus the arms gives you 30, 31. So that's why it's always 31, 31. So what's the coarse graining that we will attempt here? The coarse graining is the following. We'll take one DPD particle to represent all these. So here the coarse graining degree be 11 to 1, 21 to 1, 31 to 1. Okay? So this is the system that we simulate first, very colorful, and we do it with a molecular dynamics. You have to be careful to do take the excluded volume. So WCA potential would take into account the excluded volume for this, and then you have the finite potential for the interactions. So here's what we see from molecular dynamics for those two systems. And we simulate different densities. So what we find here in this force of the correlation function, if we look at so we have a force of the correlation function, and then we point the same color as the velocity of the correlation function and some density. So if I look at red and red, this red here and this red, at the lower density, there's a huge separation of scales. And you can see it also here. Right? One decays much faster than the other. In fact, in that case, for the density 0.4, we have a ratio of those two time scales characterized by these numbers of about 20. If I look at the denser system will have this point here, this line and this line. And we can see it much closer. If I look at the log plot, I take this intercept and this intercept, the ratio here is only less than 3. So you have a slight separation of scales as opposed to a large separation of scales. Lots of methods, when they do dimension reduction, rely on huge separation of scales. The eigenvalues have to be far apart. You cannot just mix eigenvalues. So when you mix eigenvalues, that's the hard part. There's no any approximation. So I want to examine those two systems. We will see that this system here, the lighter polymer, the smaller density, basically behaves like a Markovian system, as opposed to the denser system, which you have explicitly to include memory effects, and I'll show you that. So just a little bit of orientation of the forces. So I have a cluster like that, EIJ is this force, the parallel, as I said, is here, and we have two normal forces, because we're looking only in 3D, that's how you define the directions. So now you can construct the system, and here we have the conservative force, and you can see this is repulsive only. It's clearly defined because you have the right kernels. And this is what Paul, I think, what you were asking. This is the kernel now as a function of time, but also as a function of the configuration, but also as a function of time. So the configuration itself changes. So that will not happen if you don't have the memory effects. So in a nutshell, this is what we simulate. We take small billiards and we make them large billiards. So this is the coarse graining, right? Schematically, is what happens. And in terms of the conservative forces, this is what happens. This is a nice picture to have for this lecture. We take this small billiards are governed by interactions which are very stiff, like a Lennard-Jones potential. But these large billiards are governed by a soft potential, a repulsive only potential. Okay. And let's look at the question is the structure of this fluid the same as this? And it doesn't look the same. It doesn't really look the same, but in the probability, if you look at the probability which is expressed by G of R, the one that I introduced, shows that if you, for the two densities, if you do molecular dynamics or DPD constraint for molecular dynamics, or non-Markovian DPD, the expensive part, can be cracked a lot of times, it turns out that the fluid is the same. It turns out the equation of states for both densities is the same, no problem. And you expect that the memory effect doesn't affect the equation of state, doesn't affect the conservative part, but affects the dynamics as we see. Now, if you compare for the lower density where you have large separation of scales, if you compare the velocity of the correlation function, because if this is right, you get everything right, then you see that indeed if you use all methods, they give you identical results. In other words, if you use the non-Markovian that has extra memory, it does not contribute at all. The short time scaling is correct, the long time scaling is correct, blow it up. Here, you see it's correct. There's a little bit of an effect here. I will skip in terms of the quantities that you predict, and there's no adjustable parameters. You're within 1% error in the viscosity, in the diffusivity. The split number is always a little different, the Stokes value and so on, but the results are really, really good. I'll skip the, okay, let's see what happens as we coarse grain more aggressively. I do the same thing for 21 particles. Now the degree of, this is the most aggressive coarse graining is done for this case, 31 to 1. Now you can see that you can pick up 10% errors in viscosity. And the reason for that, you can see it here. The velocity of correlation function for 11, 21, there's a little bit of difference. And then 31, this much difference in velocity of correlation would give you 10% difference in the properties. It looks very close, people are like, oh, I'm pretty happy, engineering accuracy, but the answer is that's where this comes from. Okay.
Just a quick question. So here the error is because of the numerics, or, I mean, it is possible to build a coarse grain model at that scale that is still accurate, but it's just more difficult to obtain? Or is it just that fundamentally it's the discrepancy is because of the coarse graining is just too, because I mean you can't get any, if you tune the coefficients correctly, you can get very close to the exact.
Well, let's say that you have 1,000 thing of it's when you have this 31 point, in the molecule 31, it has sort of long arms, right? So deformability, there's lots of things, and then you model all that, the microstructure becomes much more important.
Yeah, but you're just looking at this one function, so you should be able to get that one. If you just look at the velocity population.
Yeah, but that one cluster to the other, that changes because the microstructure would affect it. That's what it's all about.
But by tuning the kernel.
Think of taking like 1,000 particles in one, a very big, right? When I say 31, this has longer arms because there's one molecule in the middle and then there's like this. So.
Yeah, I think that means we can modify the kernel and to match the property. But actually, we don't want to do that because we just do not want to have the freedom to change the kernel. If we change the kernel, definitely can improve the result. But here, the point is we sample the kernel from the data. We don't have freedom to change it. Yeah. If we change the kernel, definitely can improve the result.
I have another example where if I coarse grain very aggressively, I actually cause a phase transition. Erroneous phase transition. So as I say, coarse graining has its limits. Now, let me just quickly, because I'm running out of time, show you what happens if you use this other approach. In other words, if you think of setting up a kind of inverse problem, like I said earlier, you can do this with surrogate models using machine learning, Bayesian framework, and so on. But let's say that you, for this system with 21 to 1, coarse graining degrees of freedom, the lighter polymer, you target diffusivity and viscosity that you know from molecular dynamics, and you want to reconstruct this using a system that you parameterize like a DPD. You use a simple form of DPD, so you don't have any, so you have, let's say, gamma is one parameter and S is the other parameter. And you can vary that within some range. So this could be some random sampling within a range here. So you can build a surrogate model to do this because you need to do that many times, this optimization. And now you define an error function, delta, and you want in this space of parameters, there are only two parameters here, gamma and S, you find a minimum, and indeed there is a minimum. Sometimes there's more than one minimum, it turns out. Depends on how you set up the problem. But so that means that you actually get the end very close to what you have. There's some follow, but it turns out that from this optimization, you don't get the correct velocity of Coriolis function. You can see it's way off. and some other properties. So you're targeting two properties. Sometimes if you target more properties, which of course because of the problem,
What is SPO? Can you say again?
this stochastic optimization. So it's an inverse problem. You target.
Okay.
So you parameterize the system. You start with a simple DPD. You have some parameters. You make them random variables within a range that you know. So you're in the neighborhood, and then you run this in an inverse loop, optimization loop, and you try to find the minimum. And then you can do MCM to get the distributions of these parameters. And you can get the average of that.
Okay.
Okay. So now let's go back to this memory effect, because this is now and I'm pretty much finished with it. This is the case where we have no separation of scales. And if you go through all these exercises that I showed you before, it turns out that if you compare the velocity of correlation function, which is the metric we produce, MD is the red, blue is the DPD with memory, and green is the DPD without memory. So you can see that there's a large disparity now between the two. So this is the case as you increase the density here, you have to introduce a memory effect. So we know how to do it. The problem is really, really expensive. So you cannot try this on your laptop all the time. You need many laptops. So we recently within CM4 we have some collaborations with Eric here and his son here who's working on this to try to come up with a way to introduce memory effects for this Markovian system, but using non-Markovian dynamics. I don't have a lot of time to explain this, but here's the rough idea. You introduce an auxiliary field S. This A matrices will depend on this kernel, the memory kernel that we want to approximate, that we want to target. But by doing that, you set up this stochastic process, this classical OU process, and you can solve for S. If you substitute and you eliminate S, you see actually what's happening. You have some sort of non-Markovian dynamics using this auxiliary field F for the P and for the momentum, rate of momentum. I don't have the conservative forces here, so don't be confused with that. The art here is how exactly you approximate this kernel in terms of this submatrices A, and you may have seen by now that K decays exponentially, and that has some sort of oscillatory tail, and it seems to have some universal expression like that. So that's the idea here to approximate it like that. I can go forward. So that this is, if you do this fit, you can see this is a target and this is the fits in two different directions because we have parallel. And this is for the same system that we're talking about, the start. You can see this fitting does a good job. Having now the fit, you can go back and have it down here. The memory kernel will be approximated by something like this, and then you can construct these A matrices based on these parameters. This has not been written up yet, but let me just say the result so you see what happens, and I have one more minute. Remember, we took this summation over 1,000 time steps, so you have to store the system 1,000 time steps, or more actually. But we fade the memory a little bit. So in this system, you have to compute these matrices and so on, and as time varies. But it turns out that you can get exactly the same result as the non-Markovian system, the auxiliary. The dashed blue AUX is the auxiliary system, and that gives you the Markovian dynamics, and you can get pretty much the same result, exactly the same result. But if you compare the cost, it turns out that the cost using the auxiliary system is about 20 times faster. Now, that doesn't mean that it's cheap. It probably means that it's cheaper, or by 20 times. It means exactly 20 times cheaper than this the other approach. So the moral lesson here is if you have dense systems, if you're aggressive in coarse graining, you have to introduce memory into the system. But that's really, really expensive, so you have to have some minimalistic approaches to do it. This auxiliary system seems to be a promising method, but hasn't really been used in real systems. This is one of the first times that it has been used. I think it has been used for springs and other simpler systems. Now, one more last slide to show you, and this is some work was done by people at Quran and also Pepe Español, who is one of the founders of these DPT methods and statistical physicists. So he was a little more aggressive than us, so he coarse-grained the star polymer like 71:1. So he got a radial distribution function. This is GeoVar, which looks like this. I talked to him since then, and this may not be computed quite right, but basically he gets some of the same fluid. But here's a point that they made in the paper, which I find very, very interesting, and I mentioned that earlier. If you look at the velocity autocorrelation function versus time, and the empty system gives you that, the black curve. The DPT system for this case will give you this a little bit overdone. But if you do what's called the coarse-grained molecular dynamics, without accounting explicitly for stochastic force, without the random force, without the thermostat, you just coarse-grain the conserved part. This is what you get. You get the red curve, which looks like this, right? Now, if you integrate that for diffusivity, you get lucky. See how lucky you get, because that the integral of that you get in diffusivity. This cancels with that, almost, this cancels with that. And within engineering accuracy, the naked eye norm say, okay, this is pretty good. It works. So if you ask your colleagues, say it works. Well, it doesn't work, because the velocity correlation function is totally wrong. Some sort of averaging of that, with the right circumstances, all planets all aligned, will give you the result, but it's wrong. Okay, so whenever somebody comes and gives a talk and say, okay, I coarse-grain and I use coarse-grained molecular dynamics, ask the question, what type of coarse-graining you're doing? Are you including stochastic terms or not? If you don't include the stochastic terms, just you can leave. Just leave. All right. So there's no free lunch. So anyway, just a summary. We demonstrated here that coarse-grained models can be constructed directly from microscopic-based dynamics. It's not the only way to use Mori-Zwanzig. You will see many creative ways of doing this today. I think you learn a lot about Mori-Zwanzig. This may be confusing, but as I said, Chanho's talk will be very clear. The Markovian substance works well for soft, not so aggressive coarse graining, and also for lighter systems, not dense, not very dense systems. And then there are ways to deal with memory. Some are expensive, but now there are some techniques which seem to be working more efficiently. There's more to be done. I mean, this kind of field, as I said, the MZ tools have been used only in the last 15 years. For particle systems, they have been used only 5 years, probably. And so there's a lot to be done. Just like in the previous lecture, I have a lot of references here, including the classic Zwanzig and Mori references. Work was done about the same time in the 60s and early 60s. Español's paper, the paper of Choren here, as a pioneering paper, and many other publications. So anyway, thank you very much.